Thank you. We will start by looking at the context of where survey meters are being used and some of their main properties before we dig into the different technologies. I have excluded spectrometers and other scintillator-based detectors in this webinar, but we'll cover ion chamber, Geiger-Müller tubes, and semiconductor diodes. It is important to know that they all have their pros and cons. By the end of the webinar, I would also like to introduce our RaySafe 452, which combines some of the technologies we have looked at. I will explain what it provides in terms of measurements, behavior, and performance. But what are survey meters and what are they used for? Well, survey meters are being used wherever there are or could be radiation present to control and minimize the unnecessary radiation to staff, patients, or to the public. Within the medical field, it is common to do different types of leakage controls. This to see if the X-ray machine is leaking, giving unnecessary dose to its surrounding. Or one can do different types of wall leakage tests to make sure that the lead in the wall or in lead glass is sufficient for protecting people outside of the room. Within nuclear medicine, other types of measurements are required, still with a purpose to protect people from unnecessary radiation. After producing different types of cocktails, one needs to scan or sweep the surface to make sure there is no radioactive spill. One also needs to control treated patients to make sure their radiation levels are low enough before being released from the hospital. I guess most people understand there are X-rays in a hospital, but X-rays are also used in the non-medical field, and it is as important to make similar measurements there. Some examples of non-medical X-ray usage are non-destructive testing for detection of defects in material, weldings, and so on. There are different types of scanners in customs, airport, and border controls. Radioactive sources can be used from level control in tanks. It is common in food and pharma to look for contamination in the final product. There are plenty of different types of survey meters on the market. All of them have their own strengths and drawbacks depending on what you would like to measure. Before choosing a survey meter, one must think through what features are important for you and your specific measurement. Usually, one must prioritize since there are a few meters which ticks all the boxes. The basic question you need to ask yourself is what type of radiation are you measuring? Is it particles or photons? Is high sensitivity, the ability to detect low dose rates, important? Maybe fast response time, possible to detect fast variation, is more important. Some would like to have a wide dynamic range, meaning it can measure both high and low dose rates accurately. Or maybe it's more important to have a wide and flat energy response, so you do not need to use correction factors when measuring on different energies. There are of course other qualities that might be of importance. Do I save time, or can I get my work done more efficiently if the meter starts up in just a couple of seconds instead of having to adjust in a few minutes? Will I benefit from having a meter that is easy to use and operate? Is sound important, or could sound be helpful, whether it is for listening for radiation or setting threshold alarm levels? Do I need to export data for reports? Am I indoors or outdoors? And do I need a meter that can handle rain and dust? Is the size and weight of importance? Could I benefit from being able to switch between multiple quantities within the same meter? Before moving on to different meter designs, I would like to circle back and say a few words about energy response and the energy response graphs. I said 2 slides ago that a wide and flat energy response might be of interest, but what does that mean? More or less all survey meters have an energy response graph, and it tells us how well the survey meter performs for certain energies. One usually tries to design the meter to have an energy response close to 1 for the whole energy range. But most meters have limitations depending on the technique used. A response lower than 1 means that the meter is having a hard time measuring at that energy and would therefore underestimate the dose. Some meters have response more than 1, meaning it will overestimate the dose for some energies. Depending on type of measurements, the user must use correction factors to get more accurate readings if the response deviates from 1. Another thing I would like to mention is the size of the serving meter. All serving meters are designed to be fully irradiated, meaning they will only show accurate readings if the full area of the meter is irradiated. If only 50% of the meter is irradiated, it will underestimate the dose by 50%. On this picture, we have 3 similar meters with different areas seeing the same amount of radiation. None of the meters are fully irradiated, but the middle one with the smallest area will show the highest dose since it's closest of the 3 to be fully irradiated. The 3 meters will show the same dose if they are all fully irradiated. We will now be moving into different types of technologies used in serving meters and on a high level talk about the pros and cons of the different technologies. Let us start with ion chambers. An ion chamber is a gas-filled chamber, usually with air, but there could be other gases as well. It has a voltage applied across 2 electrodes, which creates an electric field. Radiation then ionizes the gas, ion-electron pairs are formed, and they move towards the charged plates and creates a current. This current is what's being measured, and it's related to the amount of ionizing radiation that hits the chamber. Since the ion chamber is filled with gas, it can be sensitive to changes in temperature and pressure. Correction factors must be used unless the meter can correct for it itself. Ion chambers can be designed in many different ways. For example, one way to increase the sensitivity of the meter is to make it bigger. A larger volume means more air that can be ionized, which in turn means a higher current. This makes the meter more bulky and potentially more fragile. There's also a risk that the chamber only gets partly irradiated and therefore underestimating the dose. Another way to change sensitivity is to squeeze in more air in the same volume. This can be done by pressurizing the chamber. Again, more gas equals more ion-electron pairs and a stronger current. To keep the pressure, we need thicker walls, and if the pressurization is high enough, there is a chance that the meter gets classified as hazardous material, which causes more administration and increased transportation costs. Another drawback, again depending on application, is that thicker walls stop low energy photons from reaching the chamber, meaning the meter has lower response at lower energies. This can be seen in the energy response graph of a vented and pressurized ion chamber. The green one is for the pressurized, and we can see the drop in response for lower energy photons. Another very common technology is the Geiger-Müller. Geiger-Müller tubes or GM tubes are also gas-filled chambers with a high voltage applied across 2 electrodes. The ionizing radiation that hits the GM tube generates an avalanche of ionizing events. The discharge event of the tube voltage corresponds to 1 count in a Geiger-Müller based instrument. Right after this event has happened, the GM tube is paralyzed and blind to radiation for a short period of time. This is referred to as the dead time. The tables show you the signal from an ion chamber and GM tube respectively for different amount of radiation. You can see that you have a high or low current with the ion chamber. With the GM tube, you have a high or low count rate instead. GM tubes come in all shapes and sizes. What most of them have in common is that they are more limited in dose rate range compared to ion chambers, and that they have a non-flat energy response. But what they are well suited for is measuring particles and contamination, since they usually have a very thin casing around the GM tube. Let us finish with the last technology of today, semiconducting diodes. Semiconductor diodes are usually made of high purity doped silicon. Radiation hits the diodes, free electrons are created, which gives rise to a current. This current is measured and translated to a dose. Since they are made of a solid material, the sensitivity will be up to 1,000,000 times higher compared to an ion chamber because of the higher density. This makes it possible to make the measuring part much smaller compared to an ion chamber. They are also more robust. Semiconductor diodes do not have a linear energy response, but since they can be made small, one can also create smart designs around them. By having several diodes with different filtrations, these diodes will interact with different energies of the radiation. Diodes with low filtration will mainly interact with low energy photons. Diodes with higher filtration can interact with higher energy, and so on. This makes it possible to design a system with diodes that can measure well on a wide energy range with a flat energy response. This also makes it possible to compare the signals between the different diodes and, for example, calculate the mean energy of the radiation. So let's now look at a summary of the different technologies. If we start with ion chambers, they have a wide dynamic range and are easy to produce. A way to make them more sensitive to low dose rates is to make them bigger, but bigger meters are not always convenient. Or you can pressurize them, but then they will lose response at low energies. They might also be classified as hazardous material, making them harder to ship. GM tubes have high sensitivity at a non-flat energy response. They have a limited dynamic range since they get saturated at higher dose rates. Semiconducting diodes can be made much smaller. They are more durable with a wide dynamic range and a fast response time. It may be harder to measure low dose rates due to thermal noise. But what if we could combine the advantages of each technology into one meter? A small instrument with a wide dynamic range that has a high sensitivity with a flat energy response and a fast response time. Ladies and gentlemen, I give you RaySafe 452. The RaySafe 452 is based on semiconductor diodes in combination with a GM pancake detector. We have placed the GM tube in the center of the meter where it can be used as an unfiltered, highly sensitive contamination meter if needed. The GM tube is surrounded by an array of semiconductor diodes with different filtration characteristics. They create 4 channels, which contributes to a wide and flat energy response. These diodes also gives the possibility to give you the mean energy of the measured spectrum. The way it works is that when the dose rate increases, the silicon diodes automatically take over and continue to capture dose long before the GM tube would potentially get saturated because of its limited dose rate range. This results in an instrument with a high sensitivity combined with a wide dynamic range. In front of the GM tube we have 2 different filtration lids to get a flat energy response also for the GM tube at low dose rates. One filter is for air kerma measuring in gray, rad or Röntgen, while the other one is for ambient dose equivalent measuring in sievert or REM. So this is our way to combine different technologies to be able to provide a survey meter with multiple benefits: high sensitivity, fast response time, wide dynamic range, and a wide and flat energy response. This makes it a versatile survey meter for many different applications and measurement scenarios. Here we can see the 2 energy response graphs. The upper one is for ambient dose and the lower is for air kerma. And as one can see, they cover low mammography energies all the way up to nuclear medicine and linear accelerators. One can also see that they are flat in more or less the whole energy range. Other features we have managed to create are fast startup. Most ion chambers, for example, will need to be idle for a couple of minutes after startup before being used. RaySafe 452 is ready directly after startup. It has an intuitive and easily understood interface with just a few settings. You can turn on or off sound or set alarm levels. It automatically saves data, which can be exported for reports or later processing. It has a high IP classification, meaning it can be used outdoors in rainy and dusty environments. It is handy in size and it's lightweight, and you can measure multiple quantities with the two different filtration lids. We would also like to share a recent study of RaySafe 452 made by Tohoku University in Japan. Ion chambers have strong reputation in this region, and of course people may be a little skeptical to new survey meter based on new technology. What they did was to compare RaySafe 452 with a well-known ion chamber. And what they found was actually that RaySafe 452 is as good as an ion chamber, or even better for their applications. RaySafe 452 has consistent performance similar to the ion chamber meter across all tube voltages. RaySafe 452 performs well in energy dependence and dose rate dependencies. It actually exceeds the ion chamber in dose linearity, since RaySafe 452 measures low dose rates more efficiently. Their conclusion was that the RaySafe 452 is a valuable tool for measuring scattered radiation, matching and sometimes exceeding the performance of traditional ion chamber survey meters. Its advanced features makes it a key device for enhancing radiation safety in medical environments. We would also like to share some quotes from a RaySafe 452 user. He does radiation protection measurements both in hospitals but also within the industry, such as oil refineries and non-destructive testing. And finally, one last slide showing the survey meter assortment at RaySafe and Fluke Biomedical. As you can see, they are all based on different technologies. The RaySafe 452 combines semiconductors and a GM tube. It is a versatile, multi-purpose, high-sensitivity meter that can be used for many applications, from finding spilled contamination and measuring scattered radiation from X-ray machines and linear accelerators, but also for outdoors use in high or low radiation environments. The RaySafe X2 survey sensor is based on semiconductor diodes. It is specifically made for the diagnostic X-ray room, where it's a great fit due to its small size and data capability. The Fluke 451B and 451P models are both ion chamber based, one pressurized and one vented. They are both multi-purpose meters for many applications. P, which is the pressurized version, is more sensitive, while B is vented and can also detect beta radiation. And finally, I would like to summarize the content of today's webinar by saying that, generally speaking, there is no technology that is better than the other. They all have their pros and cons, so it really depends on, first of all, how the technology is leveraged by the instrument developer, and then in what environment and for what application and purpose the instrument is used. Thank you for listening to my presentation today.
This concludes today's webinar session, and I would like to thank you, Patrik, for a fantastic presentation. And as you mentioned, a huge thank you also to our audience today. Attached to this webinar and on our website, raysafe.com, you will find even more information. Now it's time for the questions and answers section, and you are encouraged to stay with us and share your questions. If your question will not be answered today, we will get back to you via email.
Thank you so much for bringing your questions to us. You can continue to send them also during the Q&A. Let's see what our first question today is. Can the 452 measure high dose rates?
Yes. The 452 has a wide dynamic range, starting at background all the way up to 1 sievert or 1 gray an hour, which is the same as 114 Röntgen per hour. And this wide dynamic range is thanks to the combination of the GM pancake and the solid state sensors, which we presented in the presentation.
Does the 452 perform dead time correction on the GM tube?
Yes, it does. So there is no need to do any adjustments of your readings or anything like that. So you can just use it as a regular.
What is a recommended calibration interval?
Well, calibration always comes down to the user and how much the user trusts the instrument. And it also depends on how you have treated it. So we recommend a yearly calibration, which is according to many regulations, but I know there are people sending it every second year or third year as well. It depends on how it's used, more or less.
It seems like you are not heard.
I'm not heard? No sound?
No.
Strange.
I think so too.
Mm-hmm.
I wonder if I'm heard.
If we try it like this, can you hear me now? Having some technical difficulties here, but maybe you can hear me now.
Yes, we hear you.
Perfect.
Okay, so should we take it from beginning again?
Yes, let's start from the beginning again.
Yeah. Okay. Can the 452 measure high dose rates?
Yes, the 452 has a very wide dynamic range. So it can measure all the way from background up to 1 sievert or 1 gray an hour, which is 140 Röntgen per hour. And the wide dynamic range is thanks to the combination of the GM tube pancake or the GM pancake and the solid state sensors in the design of the 452.
Does the 452 perform dead time correction on the GM tube?
Yes, the 452 perform dead time correction. So there's no need for the user to adjust the readings in any way.
What is the recommended calibration interval?
Well, calibration, it always comes down to the user and how much the user actually trusts the instrument. And it may also depend on how you have treated the instrument during calibrations and so on. But we recommend a yearly calibration, which is according to most regulations. But I know there are people sending it in every second year or every third year. It depends on how it's used and how much you trust your readings.
How does the sensitivity change with the direction?
With the direction, well, the 452 has a quite good energy or dose rate response all the way out to 90 degrees of the meter, but it varies depending on the energies which you are measuring on. And well, there are very good pictures actually in the manual showing all the different angles and energies and so on. So I recommend going to the manual for all the deeper details when it comes to angular response.
In which parameters is the 452 better than the 451 P, R, Y, R, and vice versa?
Well, it depends on what you mean by parameter. I mean, the 452, it has a fast startup, meaning you can, when you start it, you can use it right away, while a 451 or more or less all ion chambers need to be idle for a minute or so before used. It also has a faster energy or dose rate response. So the 452 can detect a step in the dose rate faster than the 451, for example. And depending if you're having the P or the B version, I would say that the 452 also has a better energy response graph. The 451P, for example, has a low energy response for low energies in the mammography area, while the ambient for 452 has very flat around 1 at lower energies. And yeah, the 452 has better data capability when it comes to store and analyze the data. And those are, I guess, the main takeaways between the difference between the 451 and the 452.
Can the 452 be calibrated by an end user?
I guess it depends on what you mean by calibration. Calibration, as just looking at the dose rate response, is easy and can be done by a third-party calibration lab. They might even be able to give you a certificate, which is required for some regulations. But only the RaySafe calibration lab has the possibility to adjust the meter after the calibration or during the calibration. This means that the meter, or if the meter is out of range, only the RaySafe calibration lab will be able to adjust it. So the user are not required to use any calibration factors or correction factors or things like that.
Can it easily be cleaned from contamination?
Both yes and no. It can easily be cleaned by a damp cloth and a mild detergent, for example, as long as you clean it on the outside of the 452. If you have contamination on the inside of the meter, then it's much, much harder, especially if the GM pancake itself is contaminated. Then in worst case scenario, if you have contaminated the internals of the GM tube, we might need to actually change the GM tube.
What model should I get? I didn't understand the various models that are available.
Okay, we have 3 different models. One is the ambient dose model used for measuring in sievert or in Rem. We have one model in air kerma version used for measuring in gray, rad or Röntgen. But we also have the full version, and this version can measure the 2, which I mentioned, and can also be used as a contamination meter by removing the lid. It is only the full version that can be used as a contamination meter with a naked GM pancake.
Why in the calibration certificates doesn't appear high dose rates?
Well, when we designed the product, we did a lot of tests, of course. And we actually saw that just by adjusting at those calibration points that we have in the certificates, we are able to capture the whole energy range and the whole dynamic range of the meter. So I guess it's also, one can see it as a service to the user in this case, because if we have fewer calibration points, it means that the actual calibration process goes faster. But I can say that we are currently looking into expanding the calibration of the 452 with more dose rates. But it's actually not decided when to implement it, but we are looking into it at least.
Can the 452 be used for in-beam measurements like in the radiation field of an X-ray machine?
No, I would not recommend that, to be honest. The intention of the 452 is more of scatter radiation and leakage and things like that. So I wouldn't recommend it use it in the primary X-ray beam.
What is the directional response of the 452? It doesn't look like it captures radiation from all sides.
I think we talked about it earlier. So it has a very good response out all the way to the 90 degrees. And I recommend going to the manuals for all the deeper details of the response.
And I think that was a final question for you, Patrick. If I kind of missed something, but I don't think I did, we will get back to you via your registration email address. So I think that concludes.
We also encourage you to visit the Knowledge Center on our website at flukebiomedical.com, where you have access to complementary resources, all available to you for free to help empower you to focus on protecting lives. Thank you again for attending today's webinar, and we hope you can join us for future sessions.